In this video, we're going to look at our ability, or rather inability, to create a sequence that contains all of the real numbers in the open set 0 to 1. We're going to prove this by contradiction simply because that's the shortest route. Normally I don't like proof by contradiction. I like constructive proofs because they actually give more useful information. But what I'm going to do is I'm going to prove that no sequence of real numbers can have the whole set of real numbers in the open interval 0 to 1 by assuming that we can create such a sequence, and then I'm going to construct a number that will not be a term in the sequence. Okay? And by showing that regardless of which kind of sequence I have, right, just assuming that a sequence exists, I haven't placed any restrictions on it, but I'm going to show that I can construct a number that is not in that sequence. Therefore, no such sequence can exist. I get a contradiction disproving my original claim. So we're going to look at the decimal form of all the numbers in 0, 1. This is the most straightforward way of doing it. All the rationals are either terminating decimals, there's 0 after some point, or they repeat. All the irrationals are ones that neither terminate or repeat. And I'm also going to use mod math, okay? Mod 10 in particular, right? Because if we're using decimal, we have 10 digits, 0 through 9. Mod 10, basically it's regular addition unless something comes up to 10 or more, and if it's 10 or more, we throw out anything in the tens place or higher. So 4 plus 3 is 7. Well, 7 is 7, right? There's nothing in the tens place, there's nothing in the hundreds place, right? So the mod 10 doesn't do anything here. 9 plus 1 is 10, but it takes the 10 and the mod math gets rid of it. So we just have the number in the ones place. 7 plus 4 is 11. 11, we throw out the stuff in the tens place, and that gives us the mod math. And we're going to use this to construct our number r. Alright, so let's assume we have a sequence that has a set of terms, all of the real numbers in 0, 1, and we're going to write them in decimal form. So for every n in their natural numbers, right, we're going to have the a sub n be some decimal representation where each digit is one of the numbers between 0 for 9, right? In particular, A1, I'm going to use D11, D12, D13, D14, D1L, A2, D21, D22, D33, D24, D2L. And this is a way to keep track of which digits are in which place in which term of the sequence. Okay? Alright, so now I'm going to construct a number in decimal form as follows. So the first decimal term, R1, I'm going to add 1 mod 10 to the first decimal place of A1. Right? The first decimal place of A1 is D11. I'm going to add 1 to it mod 10. Right? What this means is that R differs from the first from A1 in the first decimal place. Therefore, it can't be equal to A1. Right? So R is not the first term in the sequence. For R2, I'm going to add 1 mod 10 to the second decimal place of A2, right, which is D22. I'm going to take, so the second decimal place of R, I'm going to take the second decimal place of the second term in the sequence. I'm going to add 1 mod 10 to it. Okay, since R is going to differ from A2 in the second decimal place, R cannot be equal to A2. Right, so we're going to continue this way. So for RL, I will add 1 mod 10 to the Lth decimal place of AL, which is going to be DLL, right? We have this nice symmetry. I'm using D11, D22, D33, D44, DLL. I'm going to add 1 mod 10 to it, right? And since R is now going to differ from the Lth term in the Lth decimal place, that means R cannot be equal to AL. So this is what we're going to construct. Right, so now I need to show, now that I've constructed R, I need to show that R is not in the set of terms. Okay, I'm going to do this also by contradiction. I'm going to assume that it is in the set of terms, okay, and prove that R contradicts that assumption. All right, so if we assume that R is a sequence, then there exists some integer k such that R is equal to AK. Right? If the two numbers are equal, well, we have two cases, right? Either they will have the same decimal representation, or one of them will be all 9s after a certain point, and the other one will be all 0s after the same place, and one greater in the prior decimal place, right? This is because, as we'll see later on in the semester, 0.999999, etc., will end up being the same as 1.000, right? This is something to mention because of the decimal representation. It's not actually going to affect our proof in this case. All right. So in the construction, the kth decimal place of R has 1 mod 10 larger than the same decimal place of A sub k. So the kth decimal place of R is DKK plus 1 mod 10. Even if it matches everywhere else, okay? Even if it matches everywhere else, it will not match on that decimal place. Therefore, it can't be equal to A sub k. Therefore, since there's nothing special about A sub k, such a term cannot exist. Therefore, R is not equal to a term of the sequence. Therefore, R is not in the sequence. Therefore, such a sequence containing all of the terms cannot exist. Right. There you go. Side note. Right. This has to do with the fact there are different kinds of infinity going on. One of them is countable. All of the rationals, all of the integers are countable. We can stick an integer next to them. Right? I showed you how to do this in class. All of the reals between 0 and 1 that potentially have these infinite decimal expansions cannot be enumerated like that. We can't associate them with the counting numbers, and that is what this shows.